Hello, everyone. Can you see the screen?
Yes, we can, Chulhi. Go ahead.
Okay, thank you. So this file I just sent out to Margaret, so maybe available soon or maybe already available.
Chulhi, sorry if I interrupt you. I think because it now takes about 50% of the screen, if you go to presentation mode, it's going to be better for the participants to follow. Thank you. And before I forget, for those again who are local, there are some Greek chocolates with almond that feel free to try, okay? Make sure you have no nut allergy, okay?
I have 3 monitors, so I have to assign correctly.
In order to present, it's best if you use the lower right symbol next to the zoom in and out icon, Chulhi.
The problem is I have 3 monitors, so it shows the presentation in the wrong screen, so I have to figure it out.
Okay.
Is it big enough?
I think that's okay.
I think it's fine. Yeah.
Okay, thank you. So the agenda is we have 3 work items, P.object recognitions. And for this project, we have 3 contributions. And also we have PV or QAM. And also we have J.NoRef. So we'll start with the P.object recognitions. So I hope the order of this presentation is correct, but I think it might be better that someone from NTT can take it from here and then present using their own screen.
Okay. Would you like to take the podium or would you like to?
No, I think they can share their screen is much better.
Yeah. So why don't you come with me? Will you be presenting, Chulhi, or just use the shares? Chulhi?
No, I'm not presenting. Yes.
You're going to present. Okay. Are you going to be talking or no? You will talk or only present? Just you need to also speak up or just share? If you want to speak up, then come with me. Yeah. Why don't you bring up the which presentation do you want? The presentation. Okay. here. You're already on the Zoom. Okay, you don't. So go here and just make it a little bit. Okay. That's okay. Okay. Use the mic.
Okay. Thank you. Okay, thank you, Chad. I'm Masanori Koike from NTT. So today we have 3 contributions. And first, I present about the validation experiment result of IPP encoding videos. And this is the contribution. And before explaining the contribution, I will explain the background from the previous standardization meeting and the validation result of the parametric model was submitted to ITUT ST12 in January 2025. And since the parametric object recognition ratio estimation model had 4 modes depending on the input of the model, a significant test for RMSE was performed between a bitrate-based baseline model and the model of each mode. And experiments with all encoding shows the significant differences between a bitrate baseline model and each mode of our model in the previous meeting. And then we received the comment at the previous standardization meeting that it was necessary to perform a significant test between modes. And we conducted a significant test for each mode. And as a result, significant differences were found between modes 1 and 2. And however, the significant differences were not found between mode 0 and 1 and mode 2 and 3. And note that the modes 0 and 2 use the packet loss rate, while the modes 1 and 3 use the frame loss rate in our proposed model. So we confirmed the result of the validation experiment, and the reason of no significant differences were observed between modes is presumed to be the high correlation between the packet loss rate and frame loss rate when using all intra as the encoding mode. And however, we think that the model has to be used in other encoding conditions. Therefore, we verified whether the same result could be obtained with video using IPP structure, and which is also used. And we conducted a subjective experiment, and results show that the correlation packet loss rate and frame loss rate is low video using IPP structure, and significant differences can be found between modes. Therefore, we think that the recommendation needs to be made for all modes in order to support various encoding methods. And this is the outline of the contribution. Then we explained about the summary of the all intra encoding validation experiment, which is conducted before the previous meeting. And in the summary of the all intra encoding, and the table 1 and 2 show the RMSE and the PCC for daytime and nighttime conditions, respectively, in these tables. And statistical tests confirmed that the proposed model significantly outperformed the baseline shown in this table 3. Also, the results of the statistical test between modes are shown in table 4. In these tables, if the TB is bigger than 0, this is the statistical. There are statistically differences And this table shows that the differences between modes 1 and 2 are significant. The differences between mode 0 and 1 and as well as mode 2 and 3 are not. And the reason there are no significant differences is considered to be the strong correlation between packet loss and the number of lost frames. And in all intra-encoding, when one packet is lost, only the corresponding frame will be lost. And this is and the figure 1 shows an example of a relationship between packet loss rate, packet loss and frame loss in all intra-encoding. And this is the packet loss and frame loss correspond to the same location. And this figure shows that a high correlation between packet loss and frame loss because the packet loss location corresponds to the frame loss location. Therefore, it is considered that no significant differences was found in mode 0 and 1 or mode 2 and 3. And also we consider the hypothesis for applying each mode of the model to the IPP encoding. And the IPP encoding is using the frame or intra-frame, also P frame, I frame and P frame. And the frame loss will propagate to the subsequent frames. And the figure 2 shows the two examples of the relationship between packet loss and frame loss in IPP encoding. And this is there are two examples of losing one packet. This is the lost packet and this is the lost packet. And but the number of lost frames is different because if they in IPP encoding mode, the frame loss propagate to the next iframe. So the number of lost frame is different. So if the processed video sequences are IPP encoded, statistically significant differences may occur when mode 0 and 1 as well as mode 2 and 3 because it is difficult to estimate lost frame rate by packet loss rate accurately. And to verify this hypothesis, we conducted another subjective experiment using IPP encoding. So this section shows the subjective experiment. And to obtain the results of the object recognition ratio, subjective experiments of training and validation were conducted in accordance with the TOR and test plan, which is submitted before in the standardization meeting. And we explained the conducted experiment briefly. And we used 80 data messages recorded by a surveillance camera mounted on the front of the car. These SRC has 4 velocity patterns from 10 km per hour to 14 km per hour with 20 videos per velocity for both training and validation sets, as shown in this table. And the tables also show the example of thumbnails. We use these videos. And the hypothetical reference circuit HRC as described in this section. And videos were encoded using FFmpeg encoder with HEVC and DOP length is 1 second. And various bit rates, frame resolutions and frame rates and velocity and packet loss rate were tested. The detail of these parameters are shown in this table 6. We verified that we conducted the subjective experiment from these setting values. And then we show the processed video sequences. And in both training or validation experiments, 72 SRCs were encoded in 4 patterns, and the 8 SRCs were used by the anchor. And in total, 296 daytime PVS were created and tested in this experiment. And this is the subjective experiment procedure, and the details of the test procedure are the same, and the test plan and the previous validation set. And the summary of the experiment procedure is that the participants monitored the video using software for object recognition. And when the participants saw that a person had stepped out onto the sidewalk, they clicked the mouse and the video stopped, and their reaction time was measured. And in this experiment, the object recognition ratio is the percentage of participants who can recognize objects in the surveillance video and click the mouse within the time it is possible to avoid a collision after the object appears. And this is the subjective experiment participant is the 128 participants. So then we explain the validation test, IPP encoding validation test. And in this experiment, before analyzing the object recognition data, participants were screened out in the same way in the previous validation experiment. And also, and same as the previous experiment, the correlation of validation data by anchor PVS is conducted, showing this equation. And the performance of the proposed model is calculated by the this corrected validation data by anchor PVS. So we show the result of the experiment in this section 4.3. And using the subjective object recognition ratio, the proposed model was validated on 296 PVS. And scatter plots of the results are shown in these figures from the mode 0 to mode 3. And in these figures, the horizontal and vertical axis show the estimated object recognition ratio and subjective object recognition ratio. And, and also the RMSE and the PCC are shown in the following table 8. So this is the RMSE and the PCC for modes 0 to 3 each. And also we obtain the results compared to baseline model. And on the basis of the validation procedure, the baseline model is computed using a simple mapping of the second order bitrate to the subjective object recognition ratio. This is also the same as the before validation or intra-encoding data. And the baseline model of performance is shown in this table. RMSE and PCC are shown in the baseline model. Then we conducted a statistical evaluation of proposed model and baseline model. Also, we conducted a statistical evaluation between modes of proposed model. The statistical test in table 11 shows the test between the baseline model and model for each mode. And the results shows that the statistical test between modes, the statistical test in table 11 shows that the proposed model is statistically better than the baseline model for all mode 0 to mode 3. And also we show the results of the statistical test between modes as shown in table 12. And the result of this test shows that the statistical differences between mode 0 and 2 are shown, and also the mode 2 and 3 are also there statistical differences. And however, there are no statistically significant differences between modes 1 and 2. As I said before, and in mode 2, frame loss information is inputted to the model, and while in mode 2, the vehicle velocity information is inputted. And in the result of the verification experiment, both of these were also important, and that's why the estimation accuracy was almost the same in both mode 1 and mode 2. And we show the detailed explanation of the verification test. So we show the factor of estimation accuracy differences between mode 2 and 3. To confirm the factor of the differences, the correlation coefficients are checked to compare between the packet loss rate and frame loss rate of all intra-encoding and IPP encoding. And this figure 5 shows the relationship between the packet loss rate and frame loss rate of this is figure 5 is all intra-encoding, and figure 6 shows the IPP encoding PVS. Also, the PCC and the PCC of all intra-encoding and IPP encoding are shown in this table. And between the packet loss rate and frame loss rate, in all intra-encoding, there is a relationship between the packet loss rate and frame loss rate, and the PCC is higher than that of IPP encoding. And the frame loss can be estimated by the packet loss rate in all intra-encoding PVS. So the estimation accuracy of modes 0 and 2 is improved in all intra-encoding PVS. And on the other hand, in the IPP encoding, the frame loss will propagate to the subsequent frames. However, the model of mode 0 and 2 cannot use the frame loss rate, so the effect of lost frame propagation cannot be considered in IPP encoding PVS. Therefore, the effect of frame loss is difficult to determine in IPP encoding. And the estimation accuracy will decrease compared to mode 1 and 3. And also, we confirm the effect of the decrease in the correlation between packet loss and frame loss on the estimation accuracy. And this table shows the RMSE and PCC of mode 2 and 3 for videos with and without packet loss. And from these tables, the RMSE without packet loss of mode 2 and 3 is the same. It's almost the same. However, the RMSE with the packet loss of mode 2 is larger than that of mode 3. In mode 3, since the frame loss rate is inputted and effect of frame loss can be considered, then the estimation accuracy of mode 3 is higher than that of mode 2 for PVS with packet loss. And this is the scatter plot of the mode 3 and mode 2 without packet loss with packet loss, and this is and finally, this is the proposal, and in this contribution, the estimation result of the validation experiment with IPP encoding videos are shown, and the results show that the mode have statistically significant differences between the baseline model and since there is a weak correlation between the packet loss rate and frame rate rate in IPP encoding, the result shows statistically significant differences between modes 0 and 1 and as well as mode 2 and 3. And depending on the encoding mode, the mode shows that the significant differences vary. Therefore, we think that recommendation need to be made for all modes in order to support various encoding methods. And this is the end of this documentation. And are there any questions for this document?
Okay, thank you very much.
Thank you.
Very much, and for the extensive works and very nice presentations. Any questions for the presenter?
Yes. Okay.
So if there's no questions, I think you can proceed with the second document.
Okay, so we show the second document in the, so we show the, and sorry. A draft recommendation on P.object recognition. So we scroll the top of the recommendation. So next we show the draft recommendation of P.object recognition. And the title of the recommendation is parametric object recognition ratio estimation model for remote monitoring of surveillance video delivered from autonomous vehicle. And the first draft of this recommendation is submitted in January 2025. Then we define the content of the recommendation and the summary and results are added in this document. So in the meeting, we explained about the updated recommendation. And first we explain about summary of this document. And this documentation provides a parametric object recognition ratio model to check whether non-observer in the monitoring center can recognize an object while viewing the video taken by an autonomous vehicle surveillance camera and delivered to the monitoring center. And this object recognition ratio can be used as an indicator to check whether the surveillance video delivered to the remote monitoring center is of sufficient quality for remote monitoring around the autonomous vehicle. Also, the input used by the model consists of information obtained from video stream and vehicle information. And this contribution has 4 different modes, which are called mode of operation. Can be used for estimating the object recognition ratio in this recommendation. And this shows the 4 modes, and mode 0 information obtained from the video stream, such as resolution, bitrate, and video frame rate, in addition to packet loss information. And mode 1 has the information obtained from video stream and the frozen video frame information based on the frame inspection. And mode 2 has the same information as mode 0, and in addition to vehicle velocity. And mode 3 has the same information as mode 1, in addition to vehicle velocity. And this is the summary of this recommendation. And then we show the scope of this section, and the general content of the scope is the same as what was submitted in the previous meeting. And we define the content of wording of this scope. And let me skip the detailed explanation of this recommendation, but this section shows the background of autonomous driving and in this. And the background of remote monitoring are shown in the scope. And also the object of the aim and object of this recommendation are shown in the scope section. So then the next section shows the references, and we have the references of ITUTP.912, and the next section shows the definitions, and we have the definitions of time-tasked method, and terms defined in this recommendation are shown in this section, and this is the object ignition ratio and target distance, required reaction time, graph-to-graph latency, and contrast latency. This is the term defined in this recommendation. So then the next section shows the abbreviations and acronyms of this recommendation. And this recommendation uses the following abbreviation and acronyms, and GOP, NHVC, PCC, PVS, RMSC, RTP, UDP, IP, and are shown in this recommendation. And then we show the areas of application of this recommendation. And the application areas for recommendation is the remote monitoring system to which surveillance video is encoded in an autonomous vehicle is delivered to the monitoring center. And regarding the general application to which the model is applicable, it has been validated under certain conditions. The conditions are detailed in the table 1 of this document. The table 1 shows the display resolution and unit time for video and network, information acquisition, and required reaction time, graph-to-graph latency and control latency, and time frame, daytime and nighttime, and weather, road surface coefficient of friction, object color and size, autonomous vehicle velocity, packet trailer concealment, packet loss rate and frame loss rate, video codec, profile, global picture, and video resolution, bitrate, and frame rate. And these are parameters of which the model has been validated. And as I said before, the model has 4 modes. And which are defined in table 2. And it is recommended to use mode 3 if possible. However, if velocity or the video frame loss information is not available, modes 0 to 2 will be used. And detailed input of the information mode is provided in section 7.1. And the next section shows the building blocks and input and output information. The building blocks of the model are shown in figure 2 below. And this recommendation uses the codec related factors per unit time, and network related factors per unit time, and vehicle related factor per unit time. This is the input. And in addition, the coefficient of the model is determined by utilizing a priori information, such as graph-to-graph latency, time frame, weather, etc. The detail of the input is shown in the following section. And this section shows the model inputs. And I.11 is the codec related factor This includes the video resolution, video bitrate, video frame rate, and per unit time for all modes. And I.12 has a network-related factors. This is the video packet loss rate per unit time, and this is used in modes 0 and 2, and the number of lost frames per unit time were used in modes 1 and 3. And I.13 has a vehicle related factors. This is the autonomous vehicle velocity, kilometers per hour per unit time. And these vehicle related factors are used in modes 2 and 3 only. And I.10 is a priori information for estimation model. And this information has the following inputs and display resolution, packet loss error concealment, and codec, and source related factors such as object color or size with a time frame, and network latency factors, glass-to-glass latency, and control latency, and reaction time factors, and camera related factors such as camera mode or focal length, field of view, image stabilization, auto-white balance, and lens flare, and load related factors. And this is, as I said before, this is used to make the coefficient of the model. And the output of the model is O.11. This is what object recognition ratio. And this model outputs the object recognition ratio from 0 to 1. As described in section 1, the object recognition ratio is defined as a percentage of observers who can recognize objects within the time it is possible to prevent the vehicle from colliding with them when these objects appear target distance away from the autonomous vehicle. Then the next section shows the model algorithm. And the model in this recommendation provides O.11 from 0 to 1. And the model consists of 4 different modes. And inputs differ between each mode. In this model, the following parameters are used in the description of the model. And T is the unit time for video and network information acquisition, and B is the video bit rate, and F is the video frame rate, R is the resolution, and V is the vehicle velocity, and L is the number of lost frames. And it is directly measured in mode 1 and 3, and since the number of lost frames are not measured in mode 0 and 2, it is estimated by packet loss rate. And P is packet loss rate per unit time, use it in mode 0 and 2, and X is the object recognition ratio if no packet loss frame are occurred. And the object recognition ratio O.11 is calculated as these equations, equation 1 and 2. And as I said before, in the modes 0 and 2 cannot use the number of lost frames. And so in mode 0 and 2, the number of lost frame is calculated, estimated as follows in these equation 3. In these equations, C1 to C3 and C11 to C13 are coefficients in the model. And in equation 2 is common to all 4 modes. However, the definition of A1 to A3 differs depending on the mode. In mode 0 and 1, the vehicle velocity cannot be used. So the A1 to A3 are calculated without velocity. And in modes 2 and 3, velocity can be used. Therefore, the coefficients A1 to A3 are calculated with using velocity. Therefore, in mode 0 and 1, A1 to A3 are calculated as equations from 4 to 6. And in mode 2 and 3, A1 coefficients A1 to A3 are calculated as equation 7, 8, and 9 using V, the velocity of the vehicle. In this equation, C4 to C10 are coefficients used in the model. And equation used per mode are listed in table 3. So mode 0 uses equation 1 to 6. Mode 1 uses equation 1, 2, and 4 to 6. Mode 2 uses 1 to 3 and 7 to 9. And mode 3 uses the equation 1, 2, and this 7 to 9. Also, the set of a priori information and coefficients are listed in table 4.0. It is the a priori information and coefficient set of mode 0 to mode 3 for each mode. The table 4.0 shows that mode 0 coefficients for daytime and nighttime. And mode 1 and table 4.1 shows the coefficient of mode 1, and table 4.2 shows the a priori information and coefficient sets of mode 2, and table 4.3 has the coefficient set of mode 3. And this recommendation has one annex and two appendix. And the annex A is the calculation of target distance. And in estimating object recognition ratio, several delays must be considered. And the glass-to-glass latency, this is the sum of delays associated with network and encoding, decoding, and display latency. And required reaction time, and this is the time between recognizing an object and sending a break command. And control latency, this is the time between sending a break command and the vehicle starting to stop. The total of latency is the sum of these glass-to-glass latency, reaction time latency, and control latency. Also, the break distance is measured given in the following equation. And using the coefficients, the coefficient of friction, the break distance is calculated. And then the target distance is defined as the distance from the surveillance camera to the object when it appears. Considering these all latencies and break distance. And this is shown in this. The target distance are calculated as this equation. And this is the figure of the estimate calculating the target distance, which is using this recommendation. And also the appendix 1 has the performance figures. And in this equation, and the root mean squared error and Pearson correlation coefficient PCC are reported in table I.0 to I.3, which is submitted in the previous meeting. The parametric object recognition estimation model per mode was validated on 296 daytime PVS and 9 PVS. And these tables are RMSCC and PCC of the model of mode 0 and 1, 2, and 3. And the value of this RMSC and PCC are submitted submitted in the previous meeting and same. And the appendix 2 has a camera related factors And this appendix presents the camera-related factors of the model used in the validation experiment, and these values of camera-related factors of each daytime and nighttime periods in the validation experiment are shown in this table, table 2.1. And in the validation experiment, these values are used to represent the value of taking surveillance video for autonomous driving. So that object can be recognized in surveillance videos with an appropriate size and appearance. And this shows time frame for time camera mode, focal length, and camera field of view, image stabilization, and camera auto-white balance, delay, and lens flare. And finally, this shows the bibliography of this recommendation. And this is the end of the recommendation. Thank you for listening. And is there any questions?
Thank you very much for the very nice presentations. Is there any questions for the presentation, for the proposed recommendation? I have one simple observation. So at the moment, this method is only applied to HEVC.
Yes. So in this recommendation is only the HEVC. So but we plan to test another encoding method such as AV1. We plan to add the we plan to take the subjective experiment in another encoding method, but we don't do the subjective test yet. So in this recommendation, we only have a HEVC coefficient.
Okay, thank you. Any other questions? Okay, so if there's no further questions, I think we can proceed with the last document.
Okay, so we show the final document. So then finally, we explain the draft supplement of P-dot object recognition. And this document provides a guideline for the use of object recognition ratio estimated by P-dot object recognition. And this supplement concerns a parametric object recognition ratio estimation model for remote monitoring. And this supplement provides an example of using the object recognition ratio estimation model at a remote monitoring center, and an example of using this model is to alert an observer when the object recognition ratio falls below a threshold. And the model uses the video stream information and vehicle information acquired per unit time and outputs the object recognition ratio per unit time. So if the video quality level is too low for safe remote monitoring, the system needs to notify the operator of the danger or stop the autonomous driving vehicle to ensure safety. Therefore, it is necessary to determine the object recognition ratio threshold to judge whether the safe remote monitoring is possible. And there are several situations in which thresholds for safe remote monitoring are determined. And when a remote monitoring system provider has an object recognition ratio criterion, for example, such as 80% or so, to be met in autonomous driving, then the threshold of the alert of the object recognition ratio is have to be set a criterion, for example, 80%. And on the other hand, if the provider does not have an object recognition ratio criterion, it is necessary to determine an object recognition ratio threshold that the provider will use. And in addition, the object recognition ratio estimation model provides the average object recognition ratio of observers. And therefore, there are observers who can recognize objects even with a low object recognition ratio videos, or the observers who cannot recognize objects even with a high object recognition ratio videos. Therefore, to determine accurate threshold for each observer, the provider needs to set the threshold according to each observer's recognition ability rather than the setting uniform threshold. Of course, in this case, although the determining the object recognition ratio threshold for each observer is costly, but it is possible to perform object recognition accurately for each observer. Also, the method to set these thresholds are under development and will be submitted in the next meeting. But this is the concept of the using the object this recommendation. And differences and definitions are shown, and how to set the threshold for object recognition ratio detailed in the submitted in the next meeting. And this is the end of the document. Is there any question? Thank you.
Okay, thank you very much. Any questions or comments?
Hi, this is
Yep.
Margaret Pinson. I have a question.
Okay.
This is actually on the previous presentation document. Could you go into a little more detail on where you see the model for autonomous driving being deployed? Where would the camera be, and where is it being analyzed? And thank you. These are very interesting documents.
Okay, so you mean that that recommendation? Okay, so yes. Alex.
The ask is to go to the appendix.
Yeah. And this to the appendix and maybe.
So I believe the question is about the general setup. Where are the cameras?
Where the camera?
Where are the different components of the system you described? Where are they going to be located?
Where the so this means
So where is the camera going to be physically located?
physically located. Okay, so yeah, the camera is located in this recommendation. So the camera is located near the in front of the autonomous vehicle, or maybe inside or outside. But the camera the surveillance camera has to show the in front of the autonomous vehicle.
And Margaret, could you please repeat the question about what exactly information you want to know about the setup?
Yes, so the parameters of this model include network impairments. And so I assume that the metric is being, the video is being analyzed outside of the car. Because if the metric were being, if the object recognition is run inside the car, I would not expect any network impairments. So I'm just curious where you're expecting this, where is the object recognition going to be run? Do you have a feeling for that? Thank you.
Hi, Margaret. This is Kazusa speaking. Thank you for your questions. Actually, our model doesn't take into account the camera parameter directly. Of course, the camera parameter depending on the quality of video, of course, but this type of the degradation can be taken by the coefficient of the model, of course. So, for example, if the camera parameter is totally different, in this case, we need to set up a new coefficient of the model. In this case, so that's our assumption.
I think that Margaret doesn't. I mean, it's not only the camera parameters, since also one of the questions was, where is the processing going to take place? So if the processing going to take place in the car, where the camera is, would there be any networking effects, so to speak?
Okay, so firstly, I need to mention about this model. This type of the model is a parametric model, not a signal-based model. So the model doesn't take the media signal directly as input. Then, of course, firstly, the camera information, video is encoded at the car. Then the encoded video is delivered to the monitoring center, the remote monitoring center. And then at the remote monitoring center, video encoded information is derived at the monitoring center. And of course, we capture the packet loss information and the encoding bitrate, frame rate, resolution, and also velocity and so on at the monitoring center.
Okay, thank you. That clarified quite a lot, I think. Margaret, are you happy with the answer?
I am. Thank you. That was very helpful.
Yes, I think the summary of this recommendation might be helpful for those who just reading this recommendation for the first time. Mm-hmm. It clearly says the objective and goal of this recommendation.
Mm-hmm.
I have a question. Are you in collaboration with like a car manufacturer to kind of discussing and reviewing the need for this recommendation?
Yeah. Sorry for interrupting. Yeah, this is Kazusa speaking again. So actually, we also discussed with us, for example, bus company, because the bus company is very interested in this remote system, because, for example, now in Japan, especially in Japan, labor problem is occurred. For example, the number of the driver is very decreasing in Japan. So very many bus companies are interested in this system. This is the reason. Also, we also tested the remote monitoring center in the, in the field, actually. And also our model is also tested in this field test. So the company, bus company also, how can I say, now also bus company operator firstly watch the video. This is actually very degraded. Also, they calculate the recognition ratio. Also, they compare the both video and the recognition rate. Also, if the video is very degraded and the recognition rate is also degraded, in this case, very correlated also. So in this case, it's very useful information. So actually, my answer is the bus company is very interested in our model. Yeah.
Okay, thank you.
Any other question or comments? Okay, if there's no further questions, so what is the next plan for this new recommendation?
Thank you, Jerry. Yeah, actually, so our original plan is that a recommendation will be consented at the next study group 12 meeting. I mean the September meeting. So I think before that, I think I need to ask you to. I need to ask you to publish this draft recommendation as TD before the study group 12 meeting for review. So this is the first very important point. And also, as you already noticed, we also provide another two contributions. One is a validation test, and the other is a supplement. As you already noticed, the supplement is not premature for approved at the September meeting, but we will prepare for the complete version of the text before the September meeting. So I think this supplement will be published as a contribution at the next study group 12 meeting. Yeah, that's my plan.
Okay, thank you very much. I will prepare the TD document for this new recommendations so they can review and hopefully will consent to this one at the next study groups 12 meetings. So thank you very much. And any other question or comments on this work item?
I have just a question. The document, will they be available on VQEG meeting files, or is there somewhere else we need to look for the documents?
Yes, okay. You can see the maybe quick we can up you can see the big quick site also.
Okay, so
Yeah.
you will send them to Margaret, so
Yes, I send it to Margaret and
okay,
he-
perfect. Thank you very much.
Thank you. And any other questions? Okay, then thank you very much for the nice presentation of study document. Now we can
you very
move. Thank you very much.
Thank you very much.
So Nori, could you stop sharing your screen? Okay, thank you. Okay, so next work item we are going to deal with is P.PVOQAMs. So I think, so who's going to present this document?
Yes, can you hear me?
Okay, so you can share your screen. I'll stop sharing my screen.
Okay, thank you. Can you see my screen?
It has
Not yet.
been loading. Yeah, just wait a few minutes. Yes, we can see it now. Please continue.
Yes, thank you. This attribution, this is Limon from China Mobile. Its contribution is about OQAM, and we updated section 4, 6, 7, 8, and 9. This basic test is based on SG13 TD115.7. And let me introduce one by one. Let's go to the modification part. We add the table, the contents, and then next we add the list of figures. And we go the section 4. Yes, this section 4, we added some abbreviation, including FOV, FR, MOS, NR. And section 6, we update.
Excuse me, please. I think it might be because I think it's some of the audience is first time for them to look at this document. Would you kindly, briefly, introduce this entire document, the goal, and what you try to do?
Okay.
Not just the proposed changes.
Okay. Okay. Let me introduce to the yes. This is object quality assessment measures of panoramic video. This is scope is about recommendation defines the objective quality assessment measures for panoramic video, achieving accurate objective estimation of the video quality of panoramic video. This is including 4 reference quality assessment measures, and is 2 used to qualitative measure the impact of compression, encoding, or add video processing on the quality of panoramic video and the condition of the having reference videos. And the other methods is no reference to quality assessment methods for panoramic video, primarily used to qualitatively measure of the impact of various video process operation on the video and the quality of panoramic videos in the absence of the reference video. And section 3 is definitions. We also define the field of the view and had multi-display and reference. And under 3.2 terms, including 4 reference quality assessment methods, is compare reference and distorted video and predict the perceptual quality of the texture video in terms of scalar value representing an objective score. And we also define no reference quality assessment method is predict the perceptual quality of the texture video without relying on pristine reference video. And section 4 is including abbreviations, 2D, 3D, FOV, FR, DMOS, HMD, IEEE, ISO, MOSNR, VMAF. And section 6 is overview. For each frame, the panoramic video under test. The planar video is first projected onto 6 viewpoints, and then each viewpoint image undergoes special feature extraction. The output of the 6 view image fused to obtain the view frame level feature vector. After video frame passes through the frame level feature extraction neural network, we can input into temporal model. From temporal model, the quality regression module integrates a form level features from the two perspectives, feature regression and quality pool, to regress the final predicted video quality score. And in section 6, we also give a figure 1. Figure 1 is processing follow of the panoramic video. It's including some function, for example, capturing, stitching, and content handling, encoding, encapsulation, transmission, and 316-degree view video player, and then the last is this player. And section 7, we give 4 reference to panoramic video assessment methods. Yes, these methods measure video quality by assessing the difference between impaired video and the reference video, which can be regarded as a measurement of the fidelity of the video information. We also introduced 2 concepts, Q-label. Q-label is the most value obtained from subjected evaluation experiments in the dataset, served as training labels from the supervised training of the model. And we also give Q predict. The model takes the impaired video and its corresponding reference video as input. It uses its feature extraction neural network to extract content informants and temporal informants from the video frames. The output feature from this network and then processed by a quality regression neural network to obtain predictor objective quality score. Yes, we quoted the Q predictor. We also give a loss function. Yes, local function is to minimizing the difference between Q predictor and the Q label. This is section 7. And section 7.1 is a described video pre-process. Yes, pre-process is about 2 parts. The first part is about described frame imagery. Frame imagery is predicted into 6 viewpoint image, and the 2 points are rated towards zenith and nadir, corresponding to the top and the bottom view, and other 4 views are rated towards the horizon, rotated horizontally to cover the entire in controversial region of the sphere corresponding to the front back, left, and right view. As you can see, the figure 3, you can this is the 6th viewpoint image in can past or the view content of the panoramic image. The next part, we introduced projection methods. Yes, a single frame of the panoramic video is depicted as a 316-degree spatial surface with a spherical coordinate system. By setting the field of the view to 19 degree forest emanate from the center of the sphere and the intersection spherical surface and two distinct points. These points connected form two arcs, which are highlighted as bright yellow arcs in figure 4. In the section point 2, we introduced feature abstraction. Yes, each view image is then processed to abstract spatial feature using a pre-treated HyperNet neural network, and the motion feature using a pre-treated slow-fast neural network. The feature from the 6 viewpoints subsequently fused to produce a feature vector for the entire video frame. Detailed description will be provided in appendix. Next, 7.3, we introduced a quality regression model. After the video frame undergo feature abstraction through the neural network, the quality regression module fused frame level feature will feature aggregation and quality polling to derive the final predict quality score for the video. And the detailed description of the model construction and the implementation from the quality regression module will provide in the appendix. And section 8 is about the reference panoramic video assessment methods. Yes, this different form for reference panoramic video assessment methods is input. In this method, the input is only includes impaired video, and the other module is similar as the for reference methods such as protection and pre-process frame level feature abstraction, neural network, and quality regression network neural network. In these methods, we also give we use the loss function to minimizing the difference of Q label and the Q predictor. And 8.1 is video pre-process is the same is the same as the detailed description in section 7.1, and 8.2 feature as abstraction is same to as the detailed description in sections 7.1, and 8.3 is same as. And next we give a title of the appendix is described model construction and the implementation of the feature abstraction and the quality regulation module, and we also provide the detail in the next meeting. Thank you. That's all. Thank you for listening. Thank you.
Okay, thank you very much for the presentation. Any questions or comments? I have one questions. So you are proposing full reference method and no reference method of panoramic videos. So do you have any experimental data that conventional full reference method or no reference method does not work for panoramic videos?
Yes, we have also is Paris, and we also detail test reports in the next meeting.
Okay. Okay, so it's interesting proposal. So I think there are some other labs might be interested. Okay, so any other questions or comments? Okay, so if there's no further question or comments, thank you very much for the presentation, and we look forward to receiving more contribution on this topic.
Thank you, Chair.
Thank you very much. So now it's 10:25 in the local time in San Francisco's area. So do you have a coffee break time, or should we continue?
We have, in 5 minutes from now, we have our coffee break. Would you like to break now, Julie?
Yes, I think it might be better because we now move to the JDA NOREF. So instead of doing
you.
5 minutes and taking coffee break, I think take coffee
Okay,
break.
so we take a break now. We resume in 20 minutes from now. It will be 10:45 local time.